Hello students, so today we are going to discuss about MEMS resonant sensors. Now these sensors are based upon the cantilever MEMS and they are used in biological, physical as well as chemical areas. Now the advantage, as you can see, there are the four advantages associated with MEMS resonant sensors. The first one, it has got a simple geometry, like it is only based upon the cantilever structure. There is a possibility of batch fabrication. You can do extreme miniaturization, and it has got high mass sensitivity. Now, the frequency of this cantilever resonant sensor is inversely proportional to square root of the mass, and so the resonant frequency will change with and without the target. And there is the sensing possibilities of not only the mass but also the viscosity, stiffness in a biological cell. Now, in a cantilever type of resonator, the problem is of non-uniform mass sensitivity. That means a mass which is at the extreme end or the free end of the cantilever will give you the maximum sensitivity, and the one which is close to the fixed end will give you the minimum sensitivity, or in sometimes no sensitivity at all. So there is a change in the mass sensitivity depending upon the location of where the target is fixed. So there is only a limited region near the tip, that near the free end, where the sensitivity is greater than 0.9. And also one requires to extract the mass with optical images of the cantilever mass distribution. So that is one of the ways by which we can reduce the variation in mass sensitivity. Or what we can do, we can limit the attachment site to the end of the cantilever. That means there is no attachment taking place apart from the free end of the cantilever. So this will reduce the mass sensitivity. Now, there is another way by which we can overcome the problem. That is, using a cantilever, instead of using a cantilever, we change the design. So this is how the design, this is a novel design it will look like. And so it has got a high spatial uniform mass sensitivity in the pedestal. And the broad thing of this novel design is that we are using folded springs. So these folded springs, they convert flexural blending into torsional blending at the folded point. Now this, so the half folded springs, they will minimize the variation of the vibration amplitude, and they will cause uniform mass sensitivity. So the difference, the deviation in mass sensitivity is recorded is only 4%. And there is a resonance sensor, so there is a vibrations, vertical vibrations, that is 160 hertz in air and 60 hertz in liquid. Now we can also use quartz crystal microbalance sensor, so it will reduce the mass reading of the viscoelastic materials, and the mass reading is increased as the stiffness of the attached mass increases, and this is called the apparent mass. And the phenomena is called the missing mass effect. The stiffness of the attached mass is considerably lower than the sensor, so there is a vibration phase of both the sensor and the material that deviates, so that the result in initial there is an effect of reducing the inertial loading value is reduced. So also there is a necessity of to measure the coupling that is taking place between the stiffness of the attached mass and the reduced mass. So we can use finite element modeling to investigate the cell's finite stiffness and the cell geometry on the apparent mass measurement, and the detection of the elastic silicon structure with the fluid medium. Now for modeling the dynamics of the submerged structure, the structural dynamics equation needs to be considered along with the fluid mass and the momentum conservation equation. So this is the equation of the mass and momentum conservation, and these two equations are used, where you can see the rho is the density, p is the pressure, g is the gravity, and u is the velocity field of the fluid. Now the vibrating submerged structure produces fluctuations in pressure and density that propagates through the fluid. So if rho 0 is initial value, then rho dash is the primed one are the fluctuations, and it also takes place in the case of pressure and density both. And if the fluid is homogeneous, initially stationary, and undergoes small amplitude motions, then those fluctuations can be expressed by these equations. So where 0 is initial value and dash the primed one are the fluctuations, as already told, that the fluctuations are assumed to be finite deviations from the initial uniform state, that is rho 0 and p 0. And when the fluid is at rest, we take the velocity field to be equal to 0. And so the mass and the momentum balance equations can be written in this form. Del square p dash is equal to 1 by c square del square p dash by t square. Now the pressure formulation fluid element is used to model transient harmonic state of the coupled fluid system. This is important, transient harmonic state. Now this there is an assumption is based upon the fact that the amplitude of the vibration is small, that is the amplitude of the vibrator is small, that is about 1.2 nanometers, compared with the dimension of the device and the fluid is indiscrete. So if the fluid is small, then the final element model of the fluid in the matrix form when written as QP double dot dash plus, so that is P double dot means P double differentiation, B single dot means single differentiation, and there is no differentiation here. So three matrices Q, C and H are being used here. They are the mass, damping and stiffness matrices, and this F2 is the external force applied, and AT W dash W double prime is interaction term. And so finite element model of the fluid. So the structure rigidity, if the structure is rigidly mounted and it is homogeneous and it is in linear elastic any material, then the body moving in the transverse direction can be written in this form, that is m w double dot plus p w dot plus kw is equal to f1 minus ap prime, where w is the displacement, m, b and k are the mass, damping and stiffness matrices, and f1 is external force, and ap dash is interaction term in the fluid. So the final equation, governing equation for the fluid and the solid elements taken into account the coupling of pressure and motion at the interface is given through this coupled equation, the fluid structure interaction. It is, we have one matrix corresponding to m minus rho 0 at 0 into q. This is for the double dot, that is double differentiation values, w double dot and b dash double dot. The second one, this is for the mass matrices, this is for the stiffness damping matrices, and this is for the stiffness matrices. The damping matrices are corresponding to only double dot and single dot, w double dot and b dot dash, whereas the stiffness is corresponding to no dot. So no differentiation with respect to time here, and those two are equal to the two external forces, external that we have taken into consideration, one for the solid and one for the fluid. So this is the final equation.